In this lesson, we have an example of calculating the induced EMF in a coil where the magnetic flux through the coil is going to be changing, and this is our first example of actually doing it mathematically. So let's see what we're given. We're told that we have a uniform B field. So we have a uniform B field directed downward into the paper in a region of space with radius 3 centimeters. So the B field is only in this circular region from R equals 0 out to capital R only. And the magnitude of that B field is changing. It's changing according to the equation that they give us here. And as I have indicated, this equation corresponds to exponential decay because we have e to the minus 7t. Now, the problem we're solving is to calculate the induced EMF in, first, a coil that's immersed within the B field, so a coil that goes only to here. In the second case, we're going to look at a coil outside the region. Both of them will have flux within the coil changing, magnetic flux changing, so induced EMF will occur. Before we go to solve this numerically, let's first just conceptually consider Lenz's law that tells us when the magnetic flux begins to change in a coil, nature reacts to oppose that change. So it establishes an induced EMF, which makes an induced current, which will make an induced B field to fight the effect that's occurring. Well, the effect that's occurring is that B field into the paper is decreasing. Again, I don't need to know mathematically how it's decreasing to analyze the concept. I just need to know it's decreasing into the paper. So the B field is going into the paper, and let's put numbers to it. It's going from 10 to 9 to 8 into the paper. So as you can see here, to fight that effect, nature is going to want to create a B induced into the paper to keep it from going from 10 to 9 into the paper. So that means I induced is going to be clockwise. E induced will also be clockwise. So no matter what I calculate mathematically with my pluses and minuses, I should get an E induced negative here. Right-hand curl, thumb into the paper. But if I drop a negative, if I make a mistake, I can always report my answer as clockwise, as shown in the diagram, because that's what is going on. All right, let's take a look at the math to solve the induced EMF in this first path, the one that's immersed. Well, we need the time rate of change of the flux, right? So let's just peek down here, right? The induced EMF is the negative d flux dt through the coil, but I can't take the derivative of the flux until I get an expression for the flux. So that is what we're going to do. Let's get an expression for the flux. Well, in general, the flux is integral b dot n hat dA. In this case, we could have just written it as b dot n hat a because we don't need to sum up the differential area. The integral of dA is a. B comes out of the integral, right, because it's uniform across that whole circular region from 0 to little r. And notice our integral only goes to little r, which is smaller than capital R, because we don't have the entire B field. We only have the B field up to little r. So that's why the flux is negative, n hat by convention is out of the paper. We get cosine of 180, which gives us our negative here. So we have our expression for the flux, right? We plugged in the exponential decay value that they gave us. So we have our equation for the flux. We can take the derivative of it, which we do. So e to the u, derivative of e to the u is e to the u du. So that's where we pick up the negative 7, right? So the derivative with respect to u of e to the u equals e to the u du. So hopefully you remember that from calculus. So we get our expression for the induced EMF, and yes, it is negative, which we knew from our Lenz's law analysis. Negative corresponds to clockwise, thumb into the paper. 0.35, we just do the math, 0.35 pi r squared e to the minus 7t. All right, notice I have very little down here in calculation for part B, and let's talk about why that's the case. That is the case because when we put our coil outside of capital R, so our coil is now out here, anywhere out here. It could be, I have it a little bit, but I also could have drawn it way out here if I wanted to, right? We're not told where to draw it, just we need for R to be greater than, little r to be greater than R. Now we have the entire B field, right? So the whole B field is 0 to capital R. So we have all of the flux into the paper. So when we calculate our flux, our calculation will be identical to what we did in part A, except instead of going to little r, now we are going to go to capital R because that's all of the flux. So as I have here, and please put this into your notes, the area that's outside the B field started with no magnetic field. It ends with no magnetic field, so there's no changing magnetic field in any of the area that's outside. So that's why it doesn't matter if we went way outside or just a little bit outside. Anything outside will not contribute to changing flux. So the calculation we make is identical to the one we have just made in part A, but little r goes to capital R. So the mathematics of this was easy. The consequences, however, are a little surprising, I think, or I always found it to be so, because if you really think about it, let's say you were standing next to a coil out here in space. There's no B field. There's no changing B field, so you have no knowledge of the flux at the center. So you're just standing in a region of space where there's no B field. If that flux in the center begins to change, you magically see current. So if that were the case, you would have no knowledge of why it occurred. You would have to assume that that coil is seeing magnetic flux somewhere. The other thing that's interesting, and you should note about these types of problems, is that physically, from a theoretical construct point of view, in physics, we allow the voltage to exist even if the current and the wire is not there. So we say that there is an induced voltage at a region of space, even if the current isn't there to be produced. So just because the flux is changing, the induced voltage is produced. If we put a wire coil down in that region of space, now we absolutely see the current and the induced B field. So hopefully you see that the mathematics is not that difficult. We have to be a little careful in terms of how much flux region of space we have, and we'll have more practice for this in homework and can talk about it in class as well.